Welcome back. Hope you're doing well. Let's go ahead and look at this last little bit of an application here when we talk about derivatives. Differentials are something that are oftentimes talked about in a beginning calculus course, but are not really the best understood. Differentials pop up when we talk about integrals and things like this. They kind of allow us to kind of do certain things and approximate in certain ways. But we want to discuss a little bit about what the differential is and how it helps us linearize functions, how it can be used in terms of approximations. We'll also discuss the Taylor's formula as a way of generalizing linearization to approximate a little bit better if we're given more degrees of freedom in how many variables, how many degrees we allow our approximating formula to have. Maybe it's not just a line, a 1-degree polynomial, maybe it's an n-degree polynomial. If so, what is a good approximation that we could use using Taylor's formula? So let's talk about first what the differential is. We start by talking about what delta is. Delta here is going to denote for us, this is the Greek letter delta, the change in x. So say, for example, x is varying from a point x1 to x2, and you can note that the change is going to be positive if that is an increase in x and negative if it is a decrease in x. So we're writing that to be x2 minus x1, if you will, final minus initial as far as the placement of x. At delta y, we can make it to be the same sort of formula, f of x2 minus f of x1. Now, we are going to say first that we have a differentiable function f in order to try and relate these two things together. In particular, whenever I write the slope of between points like x1, y1, and x2, y2, then I know that I'm trying to find delta y over delta x. This is a good enough formula for this. This is the slope of secant lines whenever I write it with respect to this formula. But the idea is that I want to write using these formulas for tangent lines, not just secant lines. Now, the differentiable dx is going to be an independent variable, and this can be given the value of any real number that I want to go through and plug in. Now, the differential dy is going to be plugged in terms of dx. So dy is going to be defined in the following way. I'll use this little colon over here to say that this is a definition, that whenever I have y equals f of x, that dy is going to be f prime of x times dx. So this can kind of be thought of a little bit as to how I would try and find this formula. For this one, delta y is going to be the slope of the secant line times delta x. Right? This is the formula that we would have if we were trying to write this in terms of, just working with deltas on two separate points. But here, I only need to plug in one point. I only need to plug in x into this function that I'm given. And the way that I calculate dy is that is f prime of x dx. Here, this, of course, being a slope of a tangent line, as we've been trying to think about it. So this is our definition here. So the idea behind this picture is this. Here we have a function that we're looking at. Let's say that this is our y equals f of x. And let's say that we are trying to do stuff at, what's a good point in which we can use? Maybe this one right here. At this point, we could start asking questions about what happens if I want to approximate what's happening at the point right up here. Well, there's a few ways that I could do that. One way is I don't even have to approximate. I can actually just plug it into the function or plug it into this function at this point here and then note the difference in y values between those 2 points. But another way that I could approximate this is I could try and draw a tangent line here at this point of the function. After drawing that tangent line, I could now go to the exact same x value on that point and note where that is and say, okay, well, as long as this distance right here is not too small, I think that I'm okay to say that this is a good enough approximation here for this function. Well, what's going on here? What is going on here? Well, the way that I could describe this formula for this point is that I'm starting at a y value that comes from looking right here. That y value right there, maybe I'm calling this the point that I'm starting from. So this could be the points. Let's see, do we have a point here? We could call this one x naught, y naught for this point. Then if I want to find the y value here of this point xy that I'm approximating, then I could say that that's going to be y equals the initial y value that I'm given plus however much it took for me in order to travel from the y-coordinate down here to the y-coordinate up here. Well, thanks to the fact that I know the slope of this line being the derivative of it, so f prime of x naught, plugging in this x value right here for that derivative, then I know that I can find the difference in y's by multiplying times the change in x. So I can multiply this times x minus x naught. In fact, if I subtract y naught, you might notice that this looks very much like the point slope form for a line where I'm plugging in the derivative of the slope of the tangent line in for m. So this is that formula that we could use to approximate a point using a linearization, a linear approximation of the points on a function. Now, where are differentials plugging in here? Remember that this is y naught plus f prime of x naught times x minus x naught. X minus x naught, that's a change in x. Final minus initial, that's going from x naught to x. So this is actually y naught plus dy. Now, if I'm actually trying to approximate the point up here, let's say x1, y1, then what's happening is that I'm saying that y1 is approximately equal to y naught plus dy, that this is an approximation here. That approximation is this y down here that I could go through and calculate. Right, so this is giving me where dy is going to be coming in. So in this case, we are saying that dx is some change in x down here, and that this value right here, this is dy. Notice here, by the way, dx and delta x are all satisfying the same role. However, dy and delta y are not satisfying the same role. Change in y is going to be change in the y values of our original points. This right here is delta y. Dy is only the change in the y values on the approximation. And that's because the way that we are relating things here is with relation to the derivative of the function at the point x naught. That's why, in order to find this approximation, we used y naught plus dy. Notice that these two things are not necessarily equal, and indeed, in many cases, are not equal to each other when our function f is not a line. But it is an appropriate approximation in many places, especially when we are testing points very close from our initial approximating point. You may recall needing to use differentials when, for example, needing to do things like estimate values like square root of 4.03. You might have seen a problem very much like this. In this instance, the reason that we say that we can get a good approximation here of this value is that we are looking at a function f, which is square root of x being applied to the number 4, 4 being a number that's close to 4.03, and pretty close to that remark. Now, square root of 4 is something that I can find very easily. That's just going to be 2. But I don't quite know how to easily calculate this y value, square root of 4.03, on that function. So instead, what I do is I linearize it. I instead try and find a tangent line to the point x equals 4 on this function, and then just find out what x equals 4.03 looks like on the line instead. So that is one way that we might go through and try and use this, is using to find y values or approximations of y values when the y values themselves are pretty tricky to find. So for example, here we can compare the values of delta y and dy with the function x squared minus 2x as x changes from 3 to 3.01. Again, an x change that is very, very small. Here, delta x is 0.01. Delta y, if I went through and just calculated what this is in terms of x equals 3.01, then I would get this change in y. It would be 0.0401. However, dy, using my formula, that is just going to be shifting over by f prime of 3 times dx. Well, f prime of 3, I know that this derivative is going to be 2x minus 2. So plugging in 3 for that, I'm just going to get 4. Times the change in x is just going to give me 0.04. So indeed, delta y and dy are very close to each other. The changes between these two things are meant to be very close. Notice that dy was easier to compute than delta y, and indeed, this is when we want to try and use linearizations. For more complicated functions, it might even be impossible to compute delta y exactly. Well, you say, John, I'm just going to use my calculator. But what is your calculator giving you? Your calculator is giving you an approximation. For example, if I know that cosine of pi is -1, how am I supposed to use that to find cosine of 3.15? Well, my answer is that I'm probably going to go to the calculator. But what the calculator is doing is that it's approximating. It's saying, okay, I know that I can only have to spit out this many decimals, so I'm going to find an approximation that's good enough up to this amount of tolerance, right? So this is what is being used whenever we try and actually find what these values are. So provided we keep delta x small, we have that delta y is approximated by our differential dy. So this gives us our formula that we're looking for to find that the function of a plus some change, that y1 that we were looking at before, is approximately equal to f of a plus the differential, which is f of a plus f prime of a times delta of x. This is exactly what we call the linearization of the function at a point. L sub a being a fixed point of x, is going to be this formula. A is the fixed point that we have all the information, we gather all our information about the function from. Here, we know that this is its y value at a. We also take the information of the derivative at a, and then we multiply times the change that we are making going from x minus a. So that is giving us this linearization. So this is the tangent line approximation of f at a. Now the question is can we do better? Could we do more if we say, okay, I don't want a line to approximate this. I want a quadratic equation to approximate this. Well, the way that we end up doing this is we start trying to apply linearization not to f, but to f prime. And that's exactly what we're going to do in Taylor's formula. Here is that Taylor's formula. Here's the theorem of it. Taylor's formula says, let's first start with a function that is n plus 1 times differentiable on I. For example, if I'm looking at something where it's just looking at maybe the first derivative, then I would need it to be 2 times differentiable. Then, whenever I'm taking a look and getting information from a fixed point, x naught, that's all the way through here, then I can approximate f of x pretty well. That is, there is going to be a point C that is somewhere in between x and x naught, such that the difference between f of x and all of this stuff, which looks kind of like more of a general formula of a linearization, the difference between these two things is given by this value right here. Now, when x and x naught are pretty close, this number is usually pretty small. Of course, it also is going to depend on how big this n plus first derivative gets, but oftentimes we find ways to control that derivative in terms of our range. But the difference between these two functions is now between a function, which could be anything, and what ends up being a polynomial. This is a kth degree polynomial because the biggest, or rather, it's going to be an nth degree polynomial, I should say, because the largest possible this value of k is allowed to be is given by this ending term for the sum. It can go to be as far as high as n. So the highest power of x that I get is x to the n. So this is a polynomial of degree, I should say at most n, because this nth derivative could be 0. This is the Taylor polynomial of order n for the function f, centered at x naught. You can check that at x naught, this is actually the function f of x naught. And what's more, you can check that the derivative of f agrees at x naught as well. That is, you can check that if I take this polynomial here and take its derivative and plug in x naught, you can check that that's the same as f prime of x naught. You can do the same thing all the way up to however many degrees exist inside of your Taylor polynomial. In general, if you have that this is p sub n, f x naught, take n derivatives of it and plug in x naught, then this is going to be the same as the nth derivative of x naught. So this is true all the way up to n. So it's true for all the intermediate values of derivatives as well. So this is in some sense trying to generalize that linearization that we were doing before. There we only needed the first derivative, and because of that, we only needed the function to be differentiable. Here we are asking for the function to be n plus 1 times differentiable in order to get an approximation using Taylor's formula. We need that n plus first derivative, not to find the Taylor polynomial, because the Taylor polynomial only has n derivatives, it only needs n degrees, but in order to figure out how close we are to the actual function. This gives us an error formula, an error function, an approximating value. How far are we in between our two values, the value that we'd like to be at versus the value that we actually approximate? That last term, by the way, is sometimes called this error function, this remainder, r sub n of f of x naught. So this is that sort of formula here. So here is Taylor's formula. Here is the Taylor's formula, right? Given from something that gives you a Taylor polynomial. Now, if you had said you had an infinitely differentiable function, well, then there's no need to stop at any point with your derivatives. You can just keep taking derivatives here. And any point at which this series exists, you can define what is known as the Taylor series of f. So these Taylor polynomials are all the partial sums of this series. In fact, oftentimes you are looking at something here that you know is going towards zero. So whenever the Taylor series exists, that is, whenever this is going towards zero, you have that if and only if. So whenever this value is going towards zero as n goes toward infinity for any given x. So this is exactly what's being said here, that for any particular value of x, that series may or may not converge. In the case of convergence, the sum may or may not be f of x, right? It only happens whenever you have particular conditions on your function f. Oftentimes, you're looking for things like smooth and things like this. Now, we do want to go through and prove this with regards to Taylor polynomials, because Taylor polynomials are good for us, especially in terms of applying the derivative, because oftentimes we don't need infinitely many terms. We only need finitely many in order to approximate our function to be as close to as where we want it to be as it needs to be. So what we do is we end up trying to prove this theorem using this sort of form. The way that we end up doing it is we define a few functions here. First, remember that our function f that we're trying to approximate is given here, and that x naught is our fixed point inside of our interval from which we're gathering all of our information. So let's fix x and I for a little bit, the point that we're going to be trying to get our approximate value at. And let's define the following functions. Let's define f of t here to be x minus t to the n plus 1 over n plus 1 factorial. This looks a lot like part of the formula that you get whenever you are looking at the error function. And let's define g of t to be f of x minus f of t minus all of this stuff. Notice that the all of this stuff that I'm referencing together with f of t, that this is actually p sub n of this function at x naught defined at the point x, or no, rather defined at the rather fixed at the point t. This is actually fixed at the point t, and then we're plugging in x. So there we go. So this is this sort of function. Now, f of x minus this is going to be the difference between those two things. So g of t here is very much like our error function. Now, the function f, going back to this little part of the remainder, is going to be infinitely differentiable on R. The function g is defined and at least differentiable by Cauchy mean value theorem. Then there's going to exist a point c that works very nicely for these two functions. Now, what we're going to do is just do some math. Clearly, f of x and g of x are going to be equal to 0 here, because at this, let's take a look here. We have that if I plugged in x for f and for g here, we would get that these values are 0. Then there's going to be a point inside of here that I'm essentially, well, we've already done that here with the mean value theorem. So then we can take derivatives of these with respect to this varying variable t that we are working with, and figure out what this sort of formula ends up looking like. Once we sum this up over k, we're going to get a notion for what the derivative of g is going to look like. A lot of stuff here is going to cancel. You're going to see a lot of telescoping sum stuff going on as we continue to add this up. For example, this subtracted term should not exist anymore once I add the next term to it. So the only thing that really should matter is the subtracted term here at the very end. Namely, that g prime of t is going to be just this negative f to the n plus 1 derivative of t divided by n factorial times x minus t to the n. Now, finally, f prime of t can also be calculated much more easily. I just have to go through and look at this formula to be given as something like this. Hence, if I go through and utilize this formula, I get that g prime of t over f prime of t is just the derivative of n plus first derivative of f t for any t not equal to x. So I can use this now to solve for g of x naught, which is going to give me this very nice formula. Now, if I plug everything in, what is f, what is g, in for this formula, then this is exactly what I end up getting. The n plus first derivative that we have there in that expression is given right here, and the rest of it comes from these functions. A neat little proof here. This is not the proof that I'm usually used to giving. Usually I use the mean value theorem on each level of the derivatives, but this is a nice, more succinct way that uses Cauchy's mean value theorem. So I like both of these sorts of derivatives, these sorts of proofs, in utilizing this sort of theorem. Now, the examples that we use Taylor's theorem for are myriad, right? We've already seen that you can get essentially differentials. You can get close to specific function values as long as you're staying close by the point on the function which you're getting most of your information from. But another thing that happens is this. Now that you have a remainder function that tells you how far away you are from the actual function, from whatever your Taylor polynomial is, you can actually now get bounds for your function in terms of polynomials. For example, this function, right, this inequality right here, you can get a bound for 1 minus x to the alpha, here alpha not just being anything here, just being some number that's greater than 1. You can get a lower bound for this by a polynomial in terms of x, thanks to the fact that you can analyze the remainder function of the first degree Taylor polynomial of 1 minus x to the alpha. Well, the first thing that we've got to do is find the first degree polynomial of 1 minus x to the alpha. So what we do is we take the first derivative here. We get minus alpha times 1 minus x to the alpha minus 1. And remember, for Taylor's formula, we need to take its derivative one more time in order to use it for the error function. So that's exactly what we'll do here. We're going to have f double prime of x equals alpha times alpha minus 1 times 1 minus x to the alpha minus 2. Now, for Taylor's formula, we're going to plug in not x, but some value c here, where c is going to be some value inside of the interval of approximation. Here, x is in between 0 and 1, so this is just going to be between 0 and x for this value. And we're going to have that these two things are equal. Here is our error, and then this is our Taylor polynomial. Notice that we get to plug in f prime of 0 and f of 0 for each of those things. So that's f of 0, and this is f prime of 0. All plugging it into that Taylor series formula, this is what we end up getting. Now, notice that the left-hand side is 1 minus x to the alpha, which we know is equal here because of Taylor's formula. And then here we have 1 minus alpha x. That's exactly this Taylor polynomial. So to show that this is greater than this, I just need to show that this is positive. If I show that this is a positive error function right here, then this means that this part is a little bit bigger than this part. So that gives me what I'm looking for. So all I have to check is this actually going to be positive? Well, remember, c is in between 0 and x, and that x is in between 0 and 1. So 1 minus c is positive. Of course, taking it to the alpha minus 2, that's still going to be a positive term. Alpha is positive since it's greater than 1. Alpha minus 1 is also positive. Everything here, in fact, is going to be positive since, again, x is going to be greater than 0. So this whole thing is positive, and the inequality follows. So that gets us everything that we need. Now, we can also get an upper bound for the same thing. If we had, instead of looking at the first degree Taylor polynomial, we could have looked at the second degree Taylor polynomial, which we already have a formula for up there. We had plugged in the fact that we are looking at 0 here for x instead of c, then we would have just gotten alpha times alpha minus 1 for that derivative. Of course, we're dividing by 2 because we have to divide by 2 factorial whenever we use Taylor's formula. And then we're going to have this error function here, which we'll separate out into its own little part. This error function here should look something like this. Notice now that, one, I'm subtracting 1 power from 1 minus c. I'm also cubing x. But I'm also multiplying times alpha minus 2, which is a negative number whenever alpha is greater than 2. Or rather, now alpha is greater than 2. I should repeat myself. Alpha is greater than 2, so each of these things are positive. And now that I'm taking this derivative, I'm going to get a negative out front from taking the derivative this many times. Well, that's always going to be a negative value, and so whenever alpha is greater than 2, I get this inequality. So whenever alpha is greater than 2, I have both a lower and an upper bound for what 1 minus x to the alpha is in terms of polynomials. And what's more, the lower bound is a first degree polynomial, the upper bound is a second degree polynomial. So I'm in some sense showing that the growth is somewhere in between these two functions for this particular function here. So that's one way that Taylor polynomials could be very useful. They can give us bounds. The error function can be helping us determine, is our estimate an overestimate or an underestimate on this domain. Another example that ends up being really useful, especially in complex analysis, is looking at the Taylor series of e to the x. The function e to the x is infinitely differentiable, and by Taylor's formula, this error function is going to go all the way down to 0. You can see here what that formula looks like down here. You have e to the c being some value in between 0 and x, so that this is a finite number. And the rest of this, x to the n plus 1 divided by n plus 1 factorial, as you increase the value for n, this value is going to go towards 0, right? And you can check that using some of our sequence stuff that we did prior to this course. So this value is going to go towards 0, and hence this is going to converge to the function itself. All right. So because this error function converges nicely, this gives us that these two functions are going to be equal to each other. That is that this Taylor series equals the function e to the x. So that's going to kind of do it for us today. This is one of the big ways that derivatives can be useful, and kind of plays a big role in many other different types of mathematics. This is one of the big places we can see a lot of things coming together that we see and are launching points for entire branches of mathematics beyond this point, including complex analysis. But here we've discussed differentials, linearization of functions, together with how we can generalize linearizations to quadratic approximation, cubic approximation, and any nth degree polynomial level of approximation. But that'll do it for me today. Thank you so much. Have a wonderful day.